Hello everyone, welcome to what will be our end of semester conceptual review. So just to give you a heads up, I'm going to go quickly through this, just kind of highlighting key information. Feel free to pause the video and take notes as you see fit. So where did we start this semester? We started with atoms, a reminder that basically everything is matter and energy. Particularly in chemistry, we are concerned about atoms the most, and so an atom itself is made up of a nucleus. The nucleus at the center of the atom contains protons and neutrons. Protons have a positive charge, electrons have a negative charge. The electrons are what move about as chemistry happens. They also form orbitals that we will talk about in a little bit. Other key things to remember: protons and neutrons are the only thing that contribute to mass within within an atom. And the relative charges of each, right? So what is matter? It is stuff. Particularly, we like to differentiate between elements and compounds in chemistry. So elements are anything that is just one thing, pure molecule or single atom. And then compounds are bonded things. So CO2 would be an example, right? Typically, we represent these atoms on the periodic table with their atomic number. That's going to be this big number here. It's always a whole number, and then they have a mass number. And a reminder that that mass number is a weighted average of the number of isotopes. And so isotopes, just as a reminder, are atoms of the same element that have a different number of neutrons. So for example, here I have carbon 12. That would tell us that carbon is always atomic number 6, but in this case it has a atomic mass of 12 exactly, meaning that 6 of the mass units come from protons, 6 then come from neutrons. And so if you ever have to find the number of neutrons, you just take the total mass number, subtract the number of protons, that gives you the number of neutrons. Also, we have different models for thinking about the atom. The one that's typically most helpful to us deals with energy shells, at least in general chemistry. And so a reminder that basically we have different energy shells. We designate those with lowercase n, where n is equal to 1, 2, or 3. And electrons can move between the shells by either absorbing or, in this case, emitting electromagnetic radiation, meaning that in order to go from a higher level to a lower level of energy, you need to get rid of some of that energy, and that energy is going to be equal to Planck's constant, which is h there, multiplied by the frequency, which is that V symbol there. Okay, and that is how we would determine our energy. Speaking of energy, we are typically concerned about energy as it relates to waves, and so that is how we find the electromagnetic spectrum. And waves have kind of two key properties that we are concerned about. I guess three if you would consider energy a property as well, which we should. But the two main properties of waves we otherwise care about are wavelength, which we designate with this lambda. That is just the length of the wave, as the name would imply. So typically in units of meters of some sort, whether it be full meters, centimeters, nanometers, can have any sort of modifier there. And then frequency, which is typically in units of hertz, which is equivalent to 1/seconds. And so those two properties are related through the speed of light, which is c there. And basically, just a reminder, big take-home point here is that the wavelength, the larger the wavelength, the lower the energy. The larger the frequency, the higher the energy. So those two are going to be inversely related. So because this bottom line has a greater frequency, aka a shorter wavelength, that would be our higher energy wave. Okay. Next up, that leads us to periodic trends on the periodic table. So again, we like to think about electrons being able to occupy these different shells. And this leads to all different sorts of trends. One of the ones we care about most is atomic radius, because that tells us a lot about basically other periodic trends that we see. Key point here is that as we add more protons as we go across a row, so let's say, for example, we look at our second row where we start with lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, you'll see that the energy to remove an electron goes up. And that is because as we go across the periodic table, our atomic radius gets smaller and smaller. Basically, as we have more of this positive charge centered in our nucleus, because we have more protons as we go up an atomic number, our atomic radius gets smaller and smaller as we go from left to right across the periodic table. That is ultimately related to basically having more protons and those protons pulling tighter on the surrounding electrons. You'll notice that once we go to the next row of the periodic table, so go from neon to sodium, we see that huge drop in energy to remove an electron, and that is, of course, because we are now in a new energy shell. So we've added another shell. That means that those electrons are quite a bit easier to remove. Okay, so if you can understand that, you can understand most of the periodic trends. It pretty much all relates back to the atomic size. Okay. One thing to contrast that with, so in the last slide we talked about atomic radius, we also have ionic radius. And so things that are shown in the red here on the left side of this diagram are cations, meaning that they all have positive charges, right? And when things lose electrons, they get smaller. And so that hopefully shouldn't be surprising based on what we said on the last slide, where the more positive charge we have, the smaller it gets. If we have ions that are positively charged, the red is the ionic radius relative to the neutral atomic radius shown in gray. And so when things are positive, they are smaller. On the flip side, in the blue, when things are negative, they get bigger, right? So if we have an anion where our atom has gained electrons, its atomic radius is going to increase because it has the same amount of positive charge, but now it has more electrons, and so it's less able to hold on to all of them, and so they kind of balloon out, okay? All right, that leads us to the periodic table itself. Just a reminder about some orbitals. So our first two columns, we have our s orbitals. That's going to be this light blue on this diagram. Then typically we care next about p orbitals, which are shown in this green. So we have what we would call the s block elements, then the p block elements, and those are 6 elements basically on the right side of the periodic table, or 6 columns, I should say, of elements. Then we have our D elements in the middle and our F elements kind of coming at the bottom there. And so one thing to point out for our S and our P orbitals, essentially the row number correlates to the energy number is the same. So 1, 2, 3 column also is the third energy level. And whatever this number is in front of our orbital type, that indicates the energy level. That is our lowercase n value. So the lower that number, the lower the energy. And so when we get to the fourth row then, we have the fourth energy level for our S and our P elements, but for D, we're still at our third energy level. Okay, so those d orbital electrons are actually going to be a bit lower in energy than our 4s or any 4p electrons we might have. Okay. As far as those trends go, we then have basically ideas around electron filling. So we would fill our 1s orbital first, then our 2s orbital, then 2p, then 3s, and 3p, then 4s. So if this sort of visual representation of how to fill things helps, then great, I would use that. Another rule then, if you were to draw an electron filling diagram, is that you always want to basically fill across orbitals of the same type. So say this was the 2p orbitals. If we have 3 of those orbitals, each is capable of holding 2 electrons, but we don't pair our electrons until we filled up all 3 of those orbitals. Okay, so that is something to keep in mind. And so an example of that is basically right here, where as we go across, we put 3 electrons in a single orbital until we get to that fourth electron, and that is when we start to pair. Okay? So just a reminder for electron filling, I would certainly expect to see that on the final. And that also leads us to a discussion of quantum numbers. So key things here are the quantum numbers n and l. If you're only going to remember two, those are the key ones. N, again, describes the energy shell. Most of the time that is the row on the periodic table until we get to our d elements again, so that middle block there. And then L describes the type of orbital. And so N will always be 1, 2, 3, 4, and then L will be N minus 1 all the way to 0. And so, for example, say we have a 3D element like this right here. In that case, we would have N being equal to 3, and then L could be equal to either 2, 1, or 0. And if L was equal to 2, it would be a D. If L is equal to 1, it'd be a P. If L is equal to 0, it would be an S orbital. M sub L will always just be plus or minus whatever our L is. So if basically N is, or if, keeping with that example, if L is equal to 2, let's say, then M sub L could be plus 2, minus 2, plus 1, minus 1, or 0. All that really tells us about is the orientation in space. This is really never used to distinguish between electrons. And then finally, we have M sub S. M sub S, no matter the element, is always going to be plus 1/2 or minus 1/2. And it doesn't really matter which is which, at least for our purposes, but it'll always be plus or minus 1/2. Okay? All right, on to valence electrons. Hopefully this is something we're super familiar with at the end of the semester here. This mainly applies to our main group elements, meaning our first 2 columns and then our last 6 columns. And essentially whatever the column number is, that is the charge you will get. So for the first 3 elements, you would end up with a positive charge. Your middle column here can be plus or minus 4. And then these last 4 will be minus 3, minus 2, minus 1. And hydrogen will more often be plus 1. And then your noble gases will just kind of be their own thing. A reminder that anytime we are forming covalent bonds, the goal is to get an octet, meaning that atoms basically share electrons so that they have 8 valence electrons in their outer valence shell. Exceptions to that are hydrogen and helium only want 2. Beryllium can be happy with 4, and boron is happy with 6. And those are the hypovalent, I guess we would say, basically less than 8. And then once we get to phosphorus, we can, of course, have hypervalent, meaning more than 8. Okay? Also a reminder, polyatomic ions, still got to know those. So if you haven't learned them by this point, I guess it might be too late, but you can always look back, try and remember them. Okay? Lewis structures, it's another thing that's going to be pretty prominent on the final, so I would recommend practicing on those with some examples that we've done in quizzes or on the homework. If you don't remember how to do those are the rules on this slide here. Basically, determine the number of valence electrons, draw a skeleton with your non-central atoms connected to the central atom through single bonds. Typically, the element that is first is basically listed as the central atom. Then place 8 valence electrons in the shells of all the atoms through the addition of lone pairs, making sure you agree with step 1, basically the total number of valence electrons. Okay. Within that, a couple things with once we draw Lewis structures, a reminder that we can have resonance structures. So resonance structures, really the only difference between them is where we place our double or triple bonds. And so SO2 is kind of a classic example here. These are the 2 resonance structures of SO2. You'll notice that the only difference is the place of the double bond, right? So on this molecule, double bond is on the right side. On this molecule, double bond is on the left side. They're the same molecule, but we have a resonance structure indicating that the reality lies somewhere between these, okay? So with regards to bonds. We can describe them in a number of ways, but we want to think about how we can describe them with regards to orbitals a lot of the time. So say we have H and F coming together to make hydrofluoric acid. We have electrons that pair up, and when electrons pair and share between these two nonmetals, we end up with something that resembles what we'd call a sigma bond. And I do want to take a moment, differentiate between our sigma bonds and our pi bonds. Reminder that our sigma bonds are going to be in the same plane, right? So these are in, if we were to draw an x, y, and z axis, these are going to be in the same plane where we have this direct overlap between our two orbitals, whereas pi bonds are going to be this indirect overlap. And another thing to note with pi bonds really only show up when we have double or triple bonds. Okay, so the first bond in any complex is always going to be a sigma bond, and then any bond after that first bond can be a pi bond. Okay, so a double bond, a triple bond will be a pi bond, but the first bond is always your sigma bond. Okay. All right, good example here is O2, where we have 1 sigma, 1 pi. Okay. With regards to that, we can also talk about orbital hybridization. And so say we have an s orbital shown in the blue here with a p orbital shown in the gray. If we end up with something that is sp hybridized, we end up with orbitals that end up looking like this. So something that is intermediate between an s and a p orbital. And that is basically what hybridization looks like. In just a moment here, we'll talk about how that relates to geometry. Okay. One other thing before we get to geometry that I do want to touch on, though, with regards to single, double, triple bonds, is that basically the way we tell something is a single, double, or triple bond by looking at it is by the bond length, right? So if you remember in lab this semester, we built a lot of these molecules in Spartan, and we had a single bond, a double bond, and a triple bond, and hopefully you noticed, going from the single to double to triple, our bond length got shorter and shorter. So as we have more bonds, our atoms get closer and closer together, right? So one other thing, or I guess with regards to polarity, we also have formal charges. So this was the formula for formal charges. Key things to remember here are basically if we have the same number of shared valence electrons, shared end valence electrons, then an atom will have a formal charge of 0. I will tell you, in this class, carbon, always going to have a formal charge of 0, right? Formal charge is also going to relate to our oxidation state for those molecules. Now that we know that language, we could talk about that. Other key ones to kind of remember, if oxygen only has 1 bond, 3 lone pairs, it'll always be -1. If nitrogen has 4 bonds, it'll be +1. And so those are the ones you'll see most often. But just wanted to bring that up. So that is formal charge when we have full positive or negative charges. We also have, of course, partial positive and partial negative charges, and that relates to electronegativity. And so electronegativity, the easiest way I think to remember it is think about things that are close to fluorine on the periodic table are going to be atoms that are very electronegative, whereas things that are further from fluorine are going to be less electronegative. The one kind of exception there is hydrogen. That is closer to something like carbon than it is to something like a metal where it is on the periodic table. So just a reminder, things that are more electronegative will end up with partial negative charges in covalent compounds, whereas things that are less electronegative will end up with a partial positive. Okay? There's a chart, again, just to help you kind of visualize electronegativity. The more red or orange something is, the more electronegative it is, and the more green it is, the more electropositive or less electronegative we could see. Okay? Right, getting into geometries then. These were some of the most common geometries we talked about, and it essentially always relates to the number of bonding groups. And so if something only has 2 bonds, it's always going to be linear. All of these, I should say, are just bonds, no lone pairs on the central atom. So if you have 3, trigonal planar. If you have 4, tetrahedral. 5, it's going to be trigonal bipyramidal. 6 is octahedral. And then if we add in these lone pairs now on the central atom, we can get these sorts of different shapes where we either end up with a seesaw, T-shaped, or linear kind of geometry. And there's a big chart, but basically I would worry most about the ones that have bonds, just bonds, no lone pairs. If you have the brain capacity to study the things that also have lone pairs on the central atom, great, but I would worry about those less than the ones that just have bonds. Okay. This also leads to basically our correlation between our hybridization, our geometry, and then what our molecule actually looks like. And so, for example, linear molecules always have sp hybridization, and they always end up with that bond angle of 180 degrees. If it's sp3 hybrid or sp2 hybridized, we always end up with that 120 bond angle. Probably the best one to know, tetrahedral. If it's sp3 hybridized, it's 109.5. Anything that's tetrahedral should be around there. And then otherwise, we tend to end up with a mixture of 90s and 120s. Okay. And just a reminder, to get something that's sp3 hybridized, we have 4 bonding groups. That means we need 4 orbitals. That's why we take 1 s orbital and 3 p orbitals, put them together to make sp3 hybrid. Okay. Right, back to another view of the periodic table. Just a reminder of where things are, how we would designate them. Key things to know: this upper right-hand corner are our nonmetals and our semimetals. As far as we're concerned, things that are semimetals behave more like nonmetals in this class than they do metals, although they can be metallic in some cases, thus their name. And everything to the left of that is going to be a metal. Okay. And when we have a bond between a nonmetal and a metal, we end up with an ionic bond. So in an ionic bond, you need charges. Just a reminder that ions are things with full positive or full negative charges. So some examples here: if we have potassium and iodine come together to make potassium iodide, and lithium and sulfur come together to make lithium sulfide. And of course, they do that in basically a predictable ratio, where sulfur, because it, if we were to go back, is in the 16th column, we know it's going to take on a charge of 2 minus. Lithium, because it's in the first column, is going to take on a charge of +1. So we know if we make lithium sulfide, we're going to have Li2s, right? And that would be our molecule. Okay. Okay, within that, shifting gears just a little bit to talk about dimensional analysis. Key things to remember here: if we go between mass and number of moles, we of course use the molar mass or molecular weight. That's something that you've done probably 100 times this semester already, so I'm not worried about that one. Where I find students tend to get confused is if you were to be asked for the number of atoms or the number of molecules, that is when you use Avogadro's number. Okay, and so you have to be a number of moles to use Avogadro's number. But once you basically are in moles, use Avogadro's number to figure out the number of molecules. If, for example, you have C6H12O6 and you need to find the number of carbon atoms, then you can use Avogadro's number to get between moles and molecules, and then you can use the chemical formula. So, for example, we have 6 carbons for every 1 molecule of C6H12 we have, so we could use the chemical formula to find the number of atoms. Okay. 2 other things that we kind of touch on there that are ratio based are percent by mass. So for example, say we had ethanol, what is the percent composition? If you're given percent by mass, key thing is to find the total molecular weight there. So we have 2 carbon atoms, 6 hydrogen, 1 oxygen. We add up all of those to find our total molecular weight, and then our percent by mass is just each element's individual weight over the total, right? So it's just a fraction, basically, a percentage, if we multiply it by 100. And so we take each proportion, multiply it by 100, that gives us our percent by mass. The opposite of that is basically the empirical formula. So if you're given percentages, say 74.9% carbon, 25.1% hydrogen, you would convert those percentages to mass. And so say carbon, 74.9 grams per 100 grams of total, because as a percentage, we know it's out of 100. And then that would leave us with that many grams of whatever substance. And then we just divide by the molecular weight to find the number of moles, divide the larger number of moles by the smaller to find our ratio, and so we have a 4-to-1 ratio. The other thing to remember there is that a molecular formula is going to maybe be different than our empirical formula. So the empirical formula is just the smallest ratio of one element to the other. So in this case, 4-to-1. But a molecular formula could be something like an 8-to-2 ratio, for example. If we had an 8-to-2 ratio, we would need to do other experiments basically to figure out the molecular weight there. But we would say that our empirical formula is still that 4-to-1. Okay? All right, into our kind of thermochemistry then. Just a reminder that if we are forming bonds, we are going to release energy. If we are breaking bonds, we're going to put energy in. And so that sets us up for our ideas around thermodynamics. Key things there are that we have a system and we have surroundings. Our system is going to be where, in chemistry, that's typically where our chemical reaction is happening, whereas the surroundings tend to be everything else, basically. We also have a boundary. We typically don't talk about the boundary, so I wouldn't worry about that. Okay? Within that, we tend to have enthalpy as our main way to quantify heat with something. So in this chemical reaction, say we have H2 and Cl2. Those are our reactants. We have to break those bonds. So that's this first step here. We are breaking the bonds between H2 and Cl2 to make H atoms and Cl atoms. Then we have to take those and recombine them to make 2 moles of HCl. So in this first step, we are putting in energy. In the second step, we are releasing energy. If we were to show the energetics of that, we have, again, positive values because we have to put energy in for these first steps of breaking Cl2 and H2's bonds. Then when we combine them, we release energy. So I would actually, so that is the total. And then when we are bond making, we release energy. So that is a negative value of kilojoules per mole. And then if we want to find the enthalpy of the reaction, we just add those two values together. We end up with our enthalpy of the reaction. Okay. So that's a quick review of thermochemistry. We also have Hess's law. We did this in lab mostly, where say we have this idea where we have some chemical reaction we want to find. We can add up chemical reactions. We can potentially reverse reactions so that things cross out to basically find our overall reaction, right? And we did this example in class. You can, of course, also look in your lab notebook for a good review of how we did Hess's law. Also had temperature, so just a reminder, we're always going to be using Celsius or Kelvin in this class, and temperature is just the average kinetic energy of our molecules, and so those molecules have 3 ways that they can express that kinetic energy, either through translation, just moving, rotating, or vibrating, okay? And so that leads us to a discussion of the things with the highest kinetic energy. That is the properties of gases. And so these are basically the main things to remember. They are easy to compress because they have lots of space between their molecules. They fill their containers and they occupy more space than liquids or solids. Something to keep in mind. So again, you're not going to have an equation sheet on this final exam, but you are going to be expected to relate concepts that are basically close to the equation. So if you can do everything on this slide, you'll be in good shape as it relates to gases. Basically, how do pressure, temperature, volume, and amount of substance relate to each other? So if we think about what happens to the pressure, if we increase the temperature, pressure should go up. If we think about what happens to the pressure if the volume is increased, the pressure should go down. So we'd say those are inversely related. What happens to the pressure if the amount of substance is increased, pressure should go up, right? And so if we do that for basically all the permutations, we should be able to have a good conceptual grasp of how gases work. And that is, of course, all related to the ideal gas law, where PV equals nRT. Basically, always make sure you're using the correct units, especially with gas. Make sure you're always in Kelvin, never in Celsius. And you also want to make sure you are in ATM. Okay, so that is a good thing to remember. One other thing with gases as it relates to kinetic molecular theory, the key takeaway from this slide is that our V's here are velocity. And so the velocity is going to be related to the square root of our molecular weight, meaning that essentially things that are bigger, things that have larger molecular weights will move slower, whereas things that are smaller will move faster. And so we see that in this graph here where we have our y-axis is just the number of particles. And so this one is related to temperature. So if we have a larger temperature, we would have a larger average kinetic energy. We would see that shift down here. This would actually be very true if we had basically a light molecule, or should I say a heavy molecule, where it's going to have a lower average kinetic energy, and then T2 here would also represent a lighter molecule, where we have a greater distribution of molecules that are moving faster on average, greater kinetic energy. Okay? All right. And that also is going to relate then to things like effusion or diffusion. Same information here, basically things that are lighter travel faster. That's why things like perfumes tend to have relatively high molecular weights, so that basically we put them on in the morning and we can smell good all day, because they're going to be slow to diffuse out and not just blasting everyone with gas for 5 minutes and then not being able to smell them the rest of the day. Okay. All right, that leads us to solutions and concentration. So for solutions, a reminder that our majority component is going to be a solvent, whereas our minority component is going to be a solute. Typically, the solute is dissolved in the solvent. We can have mixture of gases. We typically have mixtures of liquids and solids. That is most of what we will discuss. And almost always in Gen Chem, our solvent is going to be water, right? We care about concentration of solutions, and oftentimes we are most concerned about molarity. It is definitely something I would know for the final exam. Molarity is just your moles of solute divided by liters of solution. And more generally, concentration can be any amount of solute divided by any amount of solution. And we, of course, have our different units like molality, parts per million, etc. Okay. Another key thing to know that is good to remember for solutions, if you're given a volume and need to find a mass, you can do that by density. So density is just our mass over our volume. I always remember that as DMV, basically D is equal to M over V, right? So that's a good one to remember. And that leads us into our final unit here, our intermolecular forces. We have three main types of covalent forces. So everything has dispersion forces. We then have dipole-dipole interactions between things that are polar, aka have that permanent dipole. And we also have hydrogen bonds. And that is, of course, related to the Knopf monster. And then these three are all related to covalent compounds. Once we have ionic compounds, we can also have ion-dipole interactions. That's basically when salts dissolve in things like water. Then we can have ion-ion forces, which is the same thing as an ionic bond. Okay? That leads to a discussion of phase changes. Hopefully you know all these by this point. Again, the tricky ones to remember: sublimation, deposition. I feel like y'all got these 4 down, so I'm just going to skip over them for now. And so jumping back to solutions real quick, we can have things dissolve. And so when things dissolve, they go from a solid to an aqueous state. A reminder that if they're covalent, so if we have just carbon, hydrogen, oxygen, those are all nonmetals. That's a covalent compound. When it dissolves, it stays together. It doesn't dissociate. We would call that a non-electrolyte, meaning it doesn't dissociate. Whereas things that are salts, like sodium chloride, when they dissolve, they dissociate into ions. So sodium plus, chloride minus, we would call that a strong electrolyte. Basically, things that dissolve are electrolytes. Things that dissolve but don't dissociate are non-electrolytes. Okay. And again, just a kind of visual representation of what something dissolving looks like. We can have sodium chloride starting as a solid, table salt, and when it dissolves, it then has that ion dipole interaction between sodium and chloride and water. Okay. That relates to solubility. This was an example we did in class. You might see the word precipitation, a reminder that precipitation means the forming of a solid out of solution. So basically mixing two things together and getting a solid. In a lot of these solution reactions, you will end up with both of your products being aqueous and then one of your products being a solid. This was a reaction that we did in lab. If we were to write the net ionic equation of this, we take the two things that just start as dissolved in solution and then they form the solid. Whereas the reason we leave out the sodium ions, the nitrate ions on both sides is because they're both aqueous on both sides, meaning that they don't change. We would call them spectator ions. They're not actually doing any chemistry in this reaction. Okay? And that leads us to a discussion of colligative properties. And so colligative properties, when things dissolve, these are all properties related to the number of particles that dissolve. So this only is affected by solute particles. So we're comparing a solution to a pure liquid. And so our vapor pressure will go down, our boiling point will go up, our freezing point will go down, and the osmotic pressure will also go up. Okay? So just good things to know as we're heading into the final. Key things, kind of a key example of how that might look. If we have 0.5 molal of all of these different ions, key thing to note here is that our covalent compound is not going to dissociate, meaning our particle number is going to be 1, which is the I value in that change in temperature for freezing point or boiling point. That's going to be 1, and then with sodium chloride, we're going to get sodium plus, chloride minus when it dissolves, so I would be 2, and then calcium chloride, we get 1 mole of calcium 2 plus, 2 moles of Cl minus, and so that would be basically I of 3, okay? Heading into the home stretch here, we have heating and cooling curves. Key things, we're either changing phase, shown in the blue here, or temperature, shown in the red. And so we have different ways we can quantify that amount of heat. Again, you won't have these equations on the final exam, but you shouldn't need them. So if that helps take some worry off, hopefully that will be of help. I would say, again, key thing, concept, we're either changing temperature or changing phase. That's the good thing to remember here. Okay? We did math. Honestly, I will just say you don't need to remember this for the final exam. Okay? Then with solutions, we also have stoichiometry. This was a good example problem that we did in class. I would recommend working this if you want some more practice with solution stoichiometry, but I know that is pretty fresh. And also you all did well on that. So I would feel confident heading into the final exam with that one. Then just some reminders on naming of things. When we have ionic compounds, it is good to either know the charge of something. So all of these, we just look either at the column or remember that zinc is always going to be 2+ for those. And then all of these are examples where we need to indicate the oxidation state. Oxidation state is shown with Roman numerals there. And so that is only going to be true for our transition metals. Then you also need to know ammonium and possibly hydronium for the final. Okay. Then with anions, we just know they're going to have a negative charge. We take the element, we chop off the ending and add our ide, so fluoride, chloride, hydride, oxide, sulfide, phosphide, etc. And of course, that's where most of our polyatomic ions come from. So you need to know those as well. Then, if we have a purely covalent compound, we use these prefixes. Some examples we've seen: carbon tetrachloride is CCl4, diphosphorus pentaoxide is P2O5, those sorts of ideas. Okay. And oxidation numbers, I believe, is our last content we covered. Key things I bolded here: free elements. If it's just a pure element, single element, oxidation state is always going to be 0. If you have a monoatomic ion, things like Na+, Cl-, the oxidation state is just equal to their charge. Other good ones to remember are that group 1 and group 2 are always +1 and +2, unless they are pure elements. And then hydrogen, always going to be +1, oxygen, always -2. Okay? If you can remember those, you should be able to figure the rest out. And that is all. I hope that wasn't too much. Again, if you have any questions, please do let me know. Otherwise, happy studying, and I